Okay, hello everyone. Last time we started, the new topic, design of experiment, right? We talked about, some of the terminology in this DOE. Then we talked about the single factor design, right? The single factor, it's the designing of it. It's easy. Also, analyzing it is going to be easy. For example, we had tree machining, with the different speed. Then we came up with this responses. The responses were roughness. And then you can plot it and see which one is going to be the minimal, right? Sometimes, you want to develop a model, empirical model. So this is the first one, 1.2. Let's say this is roughness, right? 1.2, and then another speed. This is 100. This is 150. This is 200. 150 is, let's say, 0.8. This is this point, right? The last one is somewhere here. That is 1.5. You can connect these points, with a straight line. Or if you want to develop a model, a plot, a curve feed, and then it gives you equation. The quadratic equation you can use, with the order of 2, 3, 4. Then you can predict. That model can be used for predicting roughness with SFM at a point that is not tested, right? You want to predict, what roughness you will get, if you had SFM 120 without experimenting, right? So you do 3 tests and then you develop a model. That model, that equation, which is called empirical model, okay? That can be used for predicting roughness for a point that you did not do the test. Make sense? Any question? So this becomes useful. So it removes a lot of experiment that you would need for all these points. So you just run 3 experiments to find that model and then use it for prediction. Okay, but single factor, it's going to be tedious if you have, if you want to run the single factor experiment. If you have several factors, you have to run it for every experiment. It's going to cost you, right? The experiment is not going to be cheap. It's going to take time, resources, and the labor. So that's why, sometimes we can do multi-factor, fractional, factorial, or full factor design, okay? Full factorial design is gonna look at all possible combination of selected level of factors. Let's say if you have a factor A and that one has 2 levels, right? High and low, and factor B has 3 levels, small, medium, large. The full factorial design is going to test the combination of all of them, right? So that is going to give you 8 experiments. So this is called full factorial design. So full factorial design will be very comprehensive. You have to do all combination. You cannot skip any one. So that's why they call it full factorial. Okay. And then you can analyze each factor and see how each factor affects on the response. Then we call it main effects. For each factor, we can find the main effects. Let's say if we increase the temperature, how it's gonna affect the baking time. If the baking time is a response, or you increase the temperature in the heat treatment, how it's gonna affect the strength of the steel part, right? So that is called one factor, main effect. But sometimes you have the interaction. Let's say we have this experiment. We want to see the plant growth with respect to soil moisture and fertilizer type. So you have two factors, right? Fertilizer type and soil moisture. Let's say we use moisture 2 level, a low amount of moisture, and then fertilizer type, one can be organic, the other one is going to be inorganic. Okay, so the factor A has 2 level, right? This one. Factor B is the 2 level. Then you plant the seed in the soil with the low moisture, and then apply both organic fertilizer, that's going to be level 1 for the fertilizer, and inorganic, so that's going to be level 2. So you need to test this experiment 4 times, so to make sure we have all the combination, right? Let's say, factor A, that is the soil moisture. Factor B is fertilizer type. Low, right? Low amount of moisture. So this is test 1. Test 2. So we kept the moisture the same, and then we change the fertilizer, right? Let's say organic, and this one is inorganic. And then test 3, we're going to change the moisture high amount, test 4, this should be high, organic, inorganic. Do we need any other experiment? Now we have all combination, right? LO, LI, HO, and HI. You cannot find any other combination than these 4. So what would be the result? Low moisture and organic fertilizer. The plant will grow slowly. They will be smaller, right? So we use low moisture. Then we use low moisture, inorganic. Plant will grow slightly better than the previous one. It makes sense, low moisture, the plant requires water. Normally organic fertilizer, they have a lower growth compared to inorganic fertilizer. So low moisture, inorganic, you have better than the previous one. Third scenario, high moisture, organic fertilizer, plant grow larger, healthier than previous one. The last one is going to be high moisture, inorganic fertilizer. The plant will have the largest growth. So what do we understand from this? The main effect. What is the main effect? The main effect is that we have 2 factors, right? moisture and fertilizer. High moisture promotes better plant growth than low moisture, right? So that's the main effect of moisture. We call it main effect. And then how about the fertilizer type? The main effect for the fertilizer type, inorganic fertilizer promotes better plant growth. So these are main effect. How about interaction? Do these two have any interaction with each other? Yes, they have interaction. Interaction means the effect of fertilizer type depends on the soil moisture. If you use inorganic with a high soil moisture, you will have a better growth. So right, the high moisture condition inorganic will perform better. So it's not like if you use inorganic in low moisture, you will get the same effect as the high moisture. It depends how much moist or water that plant has. The inorganic then the fertilizer, inorganic fertilizer will perform better. So it means these two, they have interaction. They are not independent from each other. So they are dependent, right? Any question? No? Interaction. Okay. If you have K factor, let's say 2 factors and then N level, the total number of run or treatment that we need can be calculated with this equation, N times K. So we have 2 factors, 2 level, we can plug them into this equation. That gives us the number of combination of the test we need, right? 2 to the power of 2, it's going to be 4. So we need 4 experiments. If we have 3 factors and 2 level, 3 factors and 2 level, then it's going to be let's see. So you can show it like this. It's going to be 8 combination. Okay. So we may need this equation later on, later for not for this class, for Monday class, for when we are looking at more than 3 levels, 2 levels or 2 factors. So this experiment shows we had 2 level factorial design, 2 factor, 2 level, right? The cutting speed is 1 factor, another factor is a feed rate, and then in the level 1 for the cutting speed, we have the lowest speed 200, the high level is 400 meter per minute. The feed rate for level 1 is 0.1 millimeter per revolution, RPM, right? It's not RPM, it's 0.1 millimeter per revolution. The level high is going to be 0.2 millimeter per revolution. So the combination will be, K level, so you will have 4 combinations. So when we run the test, we'll see the roughness is going to be different. So what's this one? These are input, right? This is input, output. We call it also response. Later on, when you want to use a software like Design Expert or Minitab, they call the output, a response. Make sure you know what the response means. And these are all, controllable factors. When we repeat the experiment for each one, and this is, this shows the experiment, right? Run. But sometimes we want to, reduce the noise. Then we can repeat that process. And then when you repeat it, they will be the same. This factor have to be the same. You will get several responses for that level, for that run. Then you have to take an average of them and put them right here for the roughness. Make sense? You see now we are using numeric value here, but sometimes in the programs, in the software, or even in the homework, we may use symbolic, or coded level. Because we had two level, low and high, we can show them with the L. L is going to represent the low level. That for the previous example, it was 200, right? So this represents 200, and this one is going to represent, the 400, low level and high. So it's going to be easier to process, to analyze. And then the roughness, you can show, the numeric value. Okay, so that's one way. Also, we can show it with the plus minus. Minus is going to represent the low level, plus is going to be the high level. Okay, if you see, minus or plus, it's going to be the same. Because we have only two level. Sometimes if we have three level, we show 0, minus 0, plus. But for these, we use only minus and plus, or LH, or another one. Sometimes we may use, you may see -1 plus 1. All of them are going to be used, interchangeably, and they mean the same. There is no other, there is no difference. For example, this one we use L and H, and we can use it like this one, minus and plus. So that was for two factor. If you have three, factors, the chart are gonna look like this one. So I said we had 2 to the power of 3, so the n is 2, k is 3. So we're gonna have 8 combination. Experiment will be 8. Look at this one. We have 3 factors: cutting speed, feed rate, and tool material. Right? Tool material is two level carbide, high speed, steel, and then feed rate again has 2 level, 0.1, 0.2, cutting speed 200 and 400. Do you see any other combination that we could use, but we don't have it here? We have all the combination with this 3 factors. This one is somehow category, right? Different material. You can use, you can assign minus to carbide, plus to HSS, or minus 1 to here, plus 1 to here. But you just need to say it, which one is which, the description. Okay. So once we find we perform the experiment, then we find let's say, a response from the experiment, we can plot the geometric, representation of that, response. The geometric representation is going to be something, like this. You can plot two axes, and this one, let's say, that the speed. What was the other factor? Feed rate. Then speed low, right? This one, this is high, this is L, this is I. So you can put your number for the lowest speed and low feed rate here. Whatever response you find, you put it there. Okay, let's go to the previous one. What should I put here? $10, right? It's going to be 10. Correct? And then feed rate low and speed high. What would be that value? We're going to be here, right? And that is 15. So we can 15. What else? We have high speed and low feed rate, which is this point, and that is 12. The roughness, and this one is 20, right? So this is geometric, representation of this experiment. In the we call these points design point, and then we assign one. Sometimes we call it 1. So that's going to be average, starting point where you use the low level for each one. We call it 1. And then this point is called B, A. This is the design point A. And this point, this is a standard, this point is called B. And also we call this point AB. Where at point AB we have both of them at high level. You see, these two are high. As you see, this description says the let's say A is 12. It represents the average response. When you run one experiment, for the design point A, you will have only one data, so it's not going to be average. But sometimes you repeat experiment, right? And then you have to put the average of those experiments for the design point A or AB or B. Okay? So if I, in the problem, if I say draw the geometric representation of this experiment, you have to see the responses and draw a schematic like this one. One axis, low, high, and one axis for the feed rate, low and high, and these are going to be the design points. Draw these, 4 points. Okay. Why do we need them? We can use them to find the main effect of speed, main effect for feed rate, and interaction. So in this experiment, let's say this is a different data. Pressure, temperature. That is 10. A is, let me change. This is 30. Design point A is 30. Design point B is 20. And design point AB is 40. We want to see the main effect of the speed. So when we change, when we go from low level to high level, how much increase we will have in the. I'm trying to see what experiment this one was. Temperature and pressure. Let's call it, effect A. Okay. What is the main effect? When we change the pressure, yes, this is going to be temperature. When we change temperature from this one to here, what's going to happen? So you take the average of these two numbers, right? If you don't have this, let's say we didn't run the plus for B, so we had only these two values, right? The increase will be, this much, right? From here to here. But now, since we have plus, we have to take average of this one and take average of these two, and then subtract it. That is going to be the difference when you change from here to here. So the main effect of A will be average of this at this point minus average of this. Another way to show it, you can use this number, this letter, and come up with this equation. I can show you. This is going to be, this equation is going to be the same as this one. This is A, right? We need to, main effect A is minus A plus AB, right? Average of them minus B minus 1. We call this one 1. That will, you can bring 2 here, right, outside. Then you will have A plus AB minus B plus 1. Is it the same? Something. There was one problem. I could not find that equation. You know why? Any idea? I got plus sign here, but in that equation I got minus. Can you find it? What happened? So we need to take average of these two and then subtract it, from this average. A plus AB times 2, right? Divided by 2. This was, a mistake. I have to add a plus. B plus 1 divided by 2, then this is going to be minus. Now we got the same equation. So in the problem, you can use this one or you can use this one. They will be the same, but I prefer this one. It's straightforward. I can provide it in the class activity today. We have one class activity related to this one. So it says if let me plug these number in there. 1 over 2. What is A here? A is 30, right? B is 40. AB is 40. B is minus 20. And this one is tricky. Make sure you know what is this one. 1 is not 1. 1 is this, design point. You have to put, that response into equation. Do not put, 1 there. So what is it? 10, right? So you put 10 in there. So it will give you some 20. What does it mean? It means, the effective temperature. It's going to be 20 units. Whatever, responses, it's going to be 20 units. And next, we find the effect of pressure. The pressure, it's going to be horizontal. So you take average of this one, you take average of the other one. This means, when you increase the pressure from here to here, you will get, this changes, right? Let me show you how you got that equation. Effect of pressure will be x these minus this one, right? For H and x bar for L. So this is AB plus B divided by 2. This one A plus 1 divided by 2. Then you have 1 over 2 AB plus B minus A minus 1. So this is the main effect of pressure for this one. Once we plug this number in there, 1, 2, AB is 40, right? B is 20 minus 30 here, and this is 10. We should have something 10. So you got a lower number. The previous one was 20. That means speed has a larger effect on that response compared to feed rate. Oh. So since we changed the problem, I should change this. This is going to be confusion. This is temperature. This is pressure. So temperature has a larger effect. It's almost a double, right? Because we found 10 here, the main effect for pressure is 10. For the temperature was how much? 20 units. So it has a larger effect. But how about the interaction? Do they have any interaction? Interaction will be like this. You take average of these two numbers diagonal and then subtract it from each other, right? What is this one? This is where we have the plus of this factor minus of this one, and this is the plus and minus of 8, and this is going to be both positive, this is both negative. AB. So we're going to take average of AB and plus 1 divided by 2, and then this one minus A plus 1 divided by 2. So AB plus 1 minus A minus B. So once we plug these numbers in there, 40, this is 10, A is 30, B is 20, and that will be 0. It said, zero interaction. It's interesting. Zero interaction means these two parameters, they do not have any effect on each other. Let me draw, plot it in Excel. So, you have. Pressure, that was temp. This is pressure. So for temp 100, 150. Pressure is 60. Okay, so we have these, data, right? And then in this, this should not be big rate. Should be pressure. pressure 60. This one is pressure 90. Okay. So it said, when you increase the temperature, from 100 to 150, no matter what level, no matter what pressure, right? Whether you use this pressure, this is pressure 60, this one both are 60, this is 100, 90. No matter which pressure you use, you will get the same amount on the response. So these two plots are parallel. If you see parallel means they don't have the factors are going to be independent. They are not dependent. There is no interaction. So no matter in which pressure you are, you will get the same amount of increase in the response. See this one and this one, the amount is the same. But sometimes they are not going to be parallel. So this one, AB is 0. Interaction, we found it. But if I change, the response, let me change the response for one of them. This one. Let's see what happens. Now there is a interaction appears there. It means these factors, there are some interaction. You will not get the same amount of response if you go from, let's say, you go from this pressure to this one. See, if you were in this pressure, this is 60 pressure, right? And you change from 100 to 160, 150, you get this much increase, right? But if you are in the different pressure, pressure 90, and you change the temperature, you get this much. So it means there is interaction between pressure and temperature. They are not independent. You cannot say, I will get the same amount of increase. When I see it, this much, I'm going to get the same amount of increase at the 90 pressure, but it's not going to be something like that. No, it's different. So we explain that behavior as an interaction between those parameters. There is interaction between pressure and temperature. Okay. So this is geometric representation. These are the equation for two factor. You see there is one, n here, right? This n we use, if we don't repeat the experiment, we use, number 1 in this, equation, number 1. If you repeat the experiment twice, 3 times, then you have to change, this n, depending how many, repeat or replicate you have. So you have to see what the questions provide. So this is another experiment. You can test it. You see cutting speed, feed rate, and then you get roughness. And then once you plug those numbers, you can find 0.3 for main effect A, and 0.7 for interaction. And this one AB, you got 1.5. What does it mean? So for effect for B, which is feed rate, it shows you a larger number. So it means feed rate has a larger effect on the roughness compared to cutting the speed. cutting speed, did not have, much effect. You can, easily see that effect here. Let's say this one. When we increase the cutting speed from 200 to 400 and the feed rate was the same, the change was a little, right? But when we have another, let me use feed rate. This one and compare with this one. With this. Experiment 1 and 3. In experiment 1 and 3, what happened? We had cutting speed the same, right? 200, and we changed only feed rate from 0.1 to 0.2. What happened? You see, there was a larger, roughness difference. About 0.8 difference, right? Compared to this two. That was 0.4, and this is 0.8, almost double, right? So anyway, for finding the main effect of A, B, or AB, use this equation, and N is going to be the number of experiment, the number of replicate or repeat. If you want to graphically find whether your process has a experiment there is any interaction between those parameters, you can take a look at this one I showed you in that Excel. If those lines are parallel, there is no interaction between those parameters, those factors. If they have different angle, there is some interaction. So the interaction is not going to be 0 on the right one. In this one, the interaction is going to be 0. Any question? So.